All right, everybody. I'm going to start putting up these videos for you to have access to, where I take a little bit more time to go through some examples and work them out in detail with all the numbers, so that we're not rushing through examples. I know I tend to, in class, show examples in concept, and I don't put all the numbers in because it just takes a lot of time. But I know that you often need to see all the numbers worked out, and it just verifies that you're following me with the concepts if you see the numbers and your numbers match my numbers. So I understand the need for that, and I struggle with the time and need to get new material, but at the same time I need to show you how to use the tools I've taught you in a practical way. So these videos will be to augment what's done in class. If you need a little bit more than what I give you in class in terms of worked out examples, you can always turn to these. They'll be posted after lectures, and you have access to them. So let's just start. Let's begin with where we were on Valentine's Day, when I was proposed to so sweetly by Cooper, and that certainly threw me off my game. I was all aflutter after that. So let's go to the conservation of energy ideas. I'm going to work a problem that comes right out of your book. It's on page 167, example 8.8. And so a wrecking ball is pulled to one side until it is 1.6 meters above its lowest point. Neglecting all friction, what will be its velocity as it passes through its lowest point? So, a wrecking ball. Let's make a diagram here. Try to capture some of these details, a physical diagram. So there's here's a crane, and on the end of the crane we have a cable and a wrecking ball. And what they're saying is that they pull the ball back, and it's at some point where, let's put in, now I can use lime green because we're not in the room. Here's the lowest point for the ball, right here. And here's its position when it's pulled back. And they tell us that this height is 1.6 meters. Let's see if that's right. 1.6 meters. Yes, that's right. And then we're going to let it go. And obviously it's going to swing down. And when it gets to the bottom, it's going to have some velocity. And they want to know what that velocity is. And so there's the setup, okay? And they tell us they want us to ignore friction. So we don't have any of that to be concerned with. So, here's what I tried to teach you in class, and I really do encourage you to draw this diagram and fill it in with as much information as you possibly can, because this is the idea of conservation of energy. So here's kinetic energy, potential energy, and work in. Here's kinetic energy, potential energy, and work out. In this problem, let's see, we can say PE equals 0 at the bottom, the lowest point. We're free to pick the context for where the potential energy is 0, so we usually pick it at the lowest point. So any PEs that we calculate in the problem will be positive numbers. That's just kind of an easy mathematical thing to do. And we're free to do it in context. At the beginning, so this is at the start of the problem on the left-hand side. This is at the end of the problem. So this is at the top of the motion, and this is at the bottom. Right, just to keep it clear. At the top, there's 0 kinetic energy because the ball is being held. Up here, let's do this. up here at this location, the ball is stationary. It's just being held there, all right? And then we let it go. And we have, there are no, let's see, contact forces. This is a good place to talk about this. Let's just go from left to right. Potential energy, there is definitely some potential energy at the beginning. Why? Because the ball is up above the zero potential energy location. And since we're talking about potential energy, we're talking only about vertical motion or vertical position, because of the rule that says with potential energy and work energy, where we're calculating those energies from the area under a graph, the force on the graph has to be parallel to the motion. Well, the force of gravity is only vertical, so the motion must be only vertical. So they give us a 1.6 meters vertical distance above the 0 point where I said 0 was. So there definitely is potential energy here. This ball is sitting in the gravitational field of the Earth higher than the 0 potential energy point, so it must have a positive potential energy, and we're going to need to figure out what that is. Okay. Work energy is a contact energy. There's some force being applied by contact, and the object is moving in the same direction as the force. Well, there is a force of contact here, and it's the tension on this cable. The tension on the cable is pulling this ball, and there's always tension on the cable. So there is a contact force, but there's no work energy done by that force because the ball never moves in the direction. It never moves up the cable. The ball never moves up along the cable. So there's a force of contact from the cable, a tension, but there's no motion in that direction, and so there's no work energy. So I don't have any work energy being applied to the problem, and I don't have any being taken out because there's no friction. So I can just put zeros in those buckets. Okay, so let's get rid of these. And now kinetic at the bottom, there's definitely kinetic at the bottom. That's the whole point of the problem, is that the ball at the bottom is moving. It's moving fast at the bottom. So there's definitely kinetic energy at the bottom. So I put a line there showing the energy there. And there's 0 potential energy at the bottom. Why is there 0? Because I'm at the bottom, and I defined that to be potential energy 0. So there's no potential energy at the bottom at the end. So here's what we've got. We have only potential energy at the beginning and only kinetic at the end. And through the problem, we change the potential into kinetic. The process of the ball swinging down lower changes the potential energy into kinetic energy. And that's what's happening. But the amount of energy is the same. It's just that it's changing what bucket it's in. Okay? That's the idea of conservation. I can change what bucket the energy is in, but I can't change the amount. So my equation is pretty straightforward. I have to figure out the potential energy at the beginning. I have to analyze a graph, and it's going to be a weight versus height graph, because that's what I told you to analyze to get potential energy. And kinetic energy, this is pretty straightforward, 1/2 mv squared. And now we have to look and see, did they tell us the mass of the ball? And it's a 40 kilogram wrecking ball. So we have to put that in here somewhere. The mass is 40 kilograms. That was a given. And so we're going to just calculate that. And here we have to draw a graph. So let's draw a graph. There's my graph. And this is going to be weight versus height. and weight is a force, so it's newtons, and height is distance, it's in meters. And what I told you in class is going to apply. The weight of an object does not change just because I lift it higher in the gravitational field. The weight is constant. And so the weight is going to be mass times g little e. That's the weight. So I have to do a calculation. So I can do that up here. Weight equals, so I take 40 kilograms and 9.807 meters per second squared, and I get 392.3. 392 newtons, and I'm just going to round it off. You keep all the digits. I'll use some truncation here. And then height, the change in the height of the ball is going to travel 1.6 meters, and it's a vertical distance because we're dealing with height, which is vertical. And the potential energy is the area at the top. Okay? And so the area is 392 times 1.6. And I get 628. 628. So I'm going to put that in here. 628 joules. That's how much potential energy the ball has when it's at the top. And that means, if I look at my equation, that means there must be 628 joules over in the kinetic energy bucket when I'm done, because those are the only buckets that have anything in them according to conservation. And so now I can say kinetic energy equals 628, and I get some other digits here, 0.65 joules. And that has to equal 1/2 mv squared. So I need to solve this equation for the velocity. And it doesn't look like it, but I'm going to show you how you can make this into one of our special equations. So let me do this. Ke equals m over 2. I'm going to group those together. V squared. I'm just going to rewrite it like that. And now I'm going to put that into one of my equation triangles. And if we look, we see that we have multiplication here. I've got two things next to each other that are getting multiplied together. So I'm going to put m over 2 here, and I'm going to put v squared here next to each other in the triangle. And then my Ke goes up here, and now I can use that to solve for the unknown. So let me, the unknown is the v squared. That's what I don't know. So what it says to do is v squared is Ke divided by m over 2. So v squared is 628.65 joules divided by 20 kilograms. So v squared equals 20 divided, I get 31.38. 31.38. And this is going to be meters squared per second squared. Make sure you work out those units. Don't just believe me. You do the dimensional analysis. But I don't want v squared, I want v. So v equals the square root of 31.38, which is 5.6. 5.6 meters per second. And if you look in your book, chapter 8, page 168, they tell you the final velocity is 5.6 meters per second. So there you go. There's how to solve it using the ideas I taught you in lecture, using the conservation of energy ideas. We have all of this, right? The buckets. Okay, so I taught you that, and this is how you use it. Then we use the idea of potential energy is found from using the area under a weight versus height graph. We used that. And we used kinetic energy is 1/2 mv squared, right there. And we put those together, and we did some algebra. I've taught you this algebra triangle technique. So we used that, and we just solved then for what we were looking for, the 5.6 meters per second. All right, so there's an example. Let me do another one for you here. This will be example 8.9, all right? This is on page 169, another example. This will have friction and some other things in it. So let me read it. It says a 20 kilogram sled rests at the top of a 30-degree slope, which is 80 meters in length. And they show a diagram in the book. And there's a kinetic friction coefficient of 0.2. What's the velocity of the sled when it reaches the bottom? Okay, so let's capture these ideas. And we have an inclined plane. Okay, so there's the inclined plane. They tell us that this angle theta is 30 degrees. So theta is 30 degrees. They tell me that I have a sled sitting at the top, which has a mass, and the mass of the sled is 20 kilograms. And they tell me that there is the length of the hill is 80 meters. That's the length along the slope is 80 meters. They tell me that there's a coefficient of kinetic friction, which is 0.2. And they want to know how fast the sled is going at the bottom of the hill. Okay, so there's the physical diagram. All right, that's capturing all the givens. All right. Now, there's a lot of pieces to this problem, so let's just go through it and see where we are. First of all, there is a PE equals 0 at the bottom, right? PE equals 0 at the bottom. So I'm choosing my context. Before I start doing any calculations, I got to get my context straight. So where is the PE equals 0? It's at the lowest position. That's at the bottom. So clearly, now we're going to make our buckets. Now we're going to make our buckets. So we have bucket, 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 bucket. And this is kinetic potential work in, kinetic potential and work out. We've got this is at the top, this is the top, this is the bottom. That's the beginning and the end of the problem. And we have kinetic at the top is 0. The sled is just sitting at the top of the hill at the beginning. There is potential energy at the top, so I have to figure that with a graph. Weight versus height. Am I putting any work into the problem? And here's how you tell the difference between work in and work out. If there's a contact force, the work is going in if the object moves in the same direction as the contact force. Work is going out if the object moves opposite the direction of the contact force. Okay? So friction always opposes the motion, so it's a work out. And that's what we're going to have this time. We're going to have work out. So they already tell us that, so I'm just going to put in over here a certain amount of energy here. Okay? So this is a graph. This is force versus distance. That's what I told you to do to calculate the work energy, energy of contact. There's no work in, there's no force of contact which is moving with the sled. There is kinetic energy at the bottom. That's the whole point. We get the sled at the bottom is going to be moving. So let's put that in here. So when the sled gets to the bottom, it's moving. It's got a velocity final. And that's what we want to know. At the bottom of the hill, there's no potential because at the bottom of the hill, we have 0 potential energy because we set that context to be 0. So here's my conservation of energy equation. I got 2 zeros on the left, 1 0 on the right. I have 1 bucket with energy in the beginning and 2 buckets within 2 different buckets with energy at the end. So the 2 buckets here at the end, this kinetic energy bucket and this work energy bucket, those two have to add up to be the same as this potential energy bucket at the beginning. That's conservation of energy. Okay? So now I need to calculate these things. I need to calculate the potential energy and the rest. Let's do this before we go much further. How do you calculate kinetic? It's 1/2 mv squared. So that's how you calculate kinetic. The other two are some graphs, so we have to make some graphs. So let's do the potential energy first. So let's make the potential energy graph. All right. Let's make the potential energy graph. And I'm going to copy this because I'm going to have another graph for the work energy. So let's label these. This is weight versus height. And this is going to be newtons, and this is going to be meters. This will be newtons. This will be meters. This is force versus distance. Okay? And let's see. We know that the weight is constant. Okay? We know the weight is constant. And we know the weight is mass times g little e. All right? And we'll just put some labels on here. Here. Now, look. This axis here is the distance axis. Okay? This is supposed to tell me distance. What kind of distance? It's a height. Okay? It's a vertical distance. Well, let's go back to our diagram and look for vertical distances here. Where did we see vertical distances? Well, we start with the sled up here, and we end with it down here. So there's a change in the height of this much, and we don't know what that is, but we got to be able to figure it out. and it'll be 80 times the sine of 30 degrees. All right, so you got to do some trig. Make sure you understand that equation. All right. If you need to start with the definition of the sine as the side opposite divided by the hypotenuse, then you can do some algebra on it to get this equation. That's what I did. Okay. So this equation came from the definition of the sine, which is the opposite side. This is the opposite side, divided by the hypotenuse. This is the hypotenuse. I know the hypotenuse. It's 80 meters. And then I rearranged it to solve that equation for the height. And this is what I get, 80 times the sine of 30. All right? So that's going to be, let's calculate that, 80 times the sine of 30. So 30 sine, and of course, 80 times, it will be 40 meters. All right, so the change in the height is 40 meters. Okay, and the weight, we said the sled was 20 kilograms, and then G little e 9.807, and we get 196. So this is 196.14. That's the weight. And so the potential energy is the area. So this area equals the 196.14 times the 40. Gives me 7,846. 7,846. It's really 45.6, but I'm going to round off. You keep all the digits, I get to round off. And it's joules because it's energy, and it's newtons times meters, and a newton meter is a joule. You have to have those units clear, okay? So there's that. So I now know that this is 7,846 joules. And that's what these other two have to add up to be, right? Okay. This is my force versus distance graph. So this is a friction force problem. So there's friction on the sled as it slides down the hill. Where does friction come from? I need an equation for friction. So I need friction, and if we remember, F(k) equals mu k times n. Normal force. Oh boy, I'm going to have to draw a vector diagram, right? That's what that says. I'm going to have to draw a vector diagram. So let's draw the vector diagram, and it's going to be rotated. Except that didn't want to do that. Let's see. Let's try that again. All right, it's the same angle as the there we go. And we've got, let's see here. Let's do this. Let's see what thickness there. I'll do that. We have weight straight down, and we have a friction force which is up, and what else do we have? We have the normal force. That's what we're looking for, normal force. The normal force is perpendicular to the interface between the sled and the hill, and that's it. So this is the normal force. This is F(k), and this is the weight. And we know we got to draw the box. And I'll get a vector down here, which is weight y, and I'll get a vector here, which is weight x. And look, there's equilibrium in the y direction. So F net in the y direction has to be 0. So n equals weight y. Okay, here's the theta. There's my 30 degrees. So we can say N equals weight Y. That comes from equilibrium considerations. The sled never moves perpendicular to the inclined plane, so it's equilibrium in the Y direction. And we can get the Y component of the weight. And the Y component of the weight, let's just do the calculation down here. We can say N equals weight Y, and weight Y equals the weight times the cosine of 30 degrees. Why is it cosine? Because the side we're looking for is right here, and that side is adjacent to the theta. It's next to the theta. It's not opposite. Okay, it's adjacent. And let's see here. And so cosine is the right function for adjacent. So, and we know the weight, the 196.14. So let me get that. So we've got 30 degrees cosine. Now we've got 196.14. I got 169.86. 169.86 newtons. That's the normal force. So FFK is 0.2, which is the mu k, times 169.86 newtons. So FFK is 33.97. So that's my friction force. That's constant. That's constant. So I put that on here. It looks very much like the other graph that we've got. But now, this is, let me see, 33.97. This is 33.97 newtons. And now, look, this axis here, again, is distance. The question is, what distance? Well, it has to be parallel to the force. Well, which way is FFK? FFK is up along the incline. So I'm only interested in distances that are along the incline. Well, here is along the incline, and the distance along the incline is 80 meters. So that's the distance I need to put on my graph. It's parallel to the force. So this is 80 meters. And the area equals the 33.97 times the 80 is 2,718. 2,718 joules. And it's really 2717.80. So I'm rounding off. You keep all the digits. So this, let's put it in here now. Let's make sure this is clear. This is work out. This is potential energy. Okay? These are my two calculations. And so I now know that I've got 78. This number here goes up, and we put it in here, in that bucket. Our work energy goes in here, 2718 joules right there. But I know that these two, this and whatever it is here, have to add up to give me the 7,846 over here. Right? That's what my conservation equation says. Well, I can do that, right? I can figure out what that is. So I've got 7,846, 7,846. So I got 5128. So this is 5128. Let's see here. 5128 joules. So that's the kinetic energy at the bottom of the hill. And that equals 1/2 mv squared. So I can say now, come down here. So 5128 joules equals 1/2 mv squared. Solve that equation. It's the square root of 2 times 5128 joules divided by m. So the 5128, 2 times that, divided by the 20 kilograms. Yes, 20 kilograms. Right? That's right. 20 divide, and then square root 22.65. 22.65 meters per second. And let's see, what do they say in the book? Should be something. 22.6 meters per second. Okay, so there we go. That was a good problem. It had a lot of features. We had to draw back from some of our FNet calculations and vector diagrams in order to figure out friction. And we had all the new features of calculating area under a graph and kinetic energy 1/2 mv squared and conservation of energy. So there are some good examples for you with this energy stuff, putting all the pieces together that we discussed in class the other day. Hope this is helpful. And, come to class with questions, and test coming up soon. So we'll talk about getting ready for that in class today. Thanks, everybody.